Welcome back to the Johnson Space Center as our pre-flight briefings continue for the STS-120 mission. This is the EVA overview briefing to preview the spacewalks to be conducted during Discovery's visit to the International Space Station. With us to discuss all of those details is the STS-120 lead spacewalk officer, Dina Contella. Dina?
Good afternoon. Our crew and EVA team are really excited to be this close to launch, and we're ready to conduct the 4 and possibly 5 spacewalks that are upcoming on STS-120. The EVA team has 2 major space station objectives. First of all, to prep Node 2 Harmony, get it out of the payload bay, and then to prep it for its eventual move to the forward end of the lab. And the second major objective is to help with the P6 relocation task, the detach and the attach. And P6 has been sitting on Z1 for almost 7 years, so we're honored to help move it from its current location to its final destination. Also for the Space Shuttle program, we're likely to be performing a detailed test objective for tile repair techniques, and we'll be using an ablative material that's dispensed out of a gun. EVAs 1, 2, and 3 are mostly dedicated to the Harmony task and the P6 relocation. And if we get the additional EVA, we'll insert it after EVA 3 to do the tile repair DTO. And this will make 5 EVAs total, and that's the most of any EVAs. That's the most EVAs for an ISS docked mission. And then the last EVA at that point would be Peggy and Yuri's EVA, which is prepping for Node 2 relocation to the forward end of the lab. This is the first flight in which we have 5 different astronauts doing EVAs. Scott Parzynski is EV1, and he has 3 previous spacewalks on STS-86 and STS-100, and he'll be conducting 4 on STS-120. He'll be wearing solid red stripes in his suit. Doug Wheelock is EV2, and he'll be performing his first EVAs on the 1st, 3rd, and 4th STS-120 spacewalks with Scott, the 4th assuming that we also get the additional EVA. And for Doug Wheelock, we call him Wheels for short, so hopefully he won't mind if I call him Wheels during this presentation. These are his first EVAs, as I've said, and he'll be wearing an all-white spacesuit. Dan Tani is EV3, and he'll be performing his second spacewalk, and he did one on STS-108. He'll be performing one with Scott, that's EVA2, and he'll be wearing broken red stripes. Peggy Whitson, the space station commander, is EV4, and she'll be leading up the 5th spacewalk, again, assuming that we have 5. She's also EVA experienced, having done a Russian EVA in an Orlan spacesuit on Expedition 5. She'll be wearing both a red stripe and a candy cane stripe. Yuri Malinchiko, the space station flight engineer, will also go out on the 5th EVA, and he's the first shuttle mission, or I guess the first EV5 for one of these missions. He's previously performed 2 Russian EVAs on board the Space Station Mir, and he's done a U.S. EVA on STS-106. He'll go out with candy cane stripes on his spacesuit. I'll also mention somebody else on the crew that has a really big role in our EVAs is Paolo Nespoli, our Ivy crew member, who will be choreographing 4 of the 5 spacewalks. There's a huge team of people that contribute to the mission and to our EVA team, but I'd specifically like to recognize my team of Allison Bollinger, the detailed EVA timeliner, and Sarah Kazukowicz-Corona, our spacesuit and airlock expert. EVA 1 will be performed by Scott and Wheels, and it's expected to go 6.5 hours long. And I think that the videos best describe the EVAs, so if we could roll the first one. Here we're zooming in to see the airlock Quest. Stephanie and Dan will position Canadarm2 for EVA operations so that the tip of the arm is near the airlock, and you can see the arm in position in the lower left. Scott will come out of the hatch first, followed by Wheels, and you can see the handrails flashing around the hatch. The first task on the EVA is to release the S-band antenna from Z1 so it can be transferred to the shuttle payload bay. They perform a leapfrog technique where Wheels holds it, then Scott holds it while Wheels moves to get into the arm, and then Scott hands it back off to Wheels. Here, Scott's high on the airlock, and Wheels is in the lower left receiving the antenna. This is video of Wheels holding the antenna so you can get a sense of scale. It weighs about 228 pounds. Wheels then begins a long ride down to the shuttle payload bay, riding Canadarm2, while Scott translates down to the payload bay free float to meet him. Scott will arrive first, and he'll begin prep work for later tasks in the payload bay. But he'll drop what he's doing when Wheels gets there, so they can together install the antenna on the carrier that you see flashing in the payload bay. Wheels will be directing the arm drivers, Stephanie and Dan, to position him close to Scott and the carrier. Here you see Scott on the left side of the picture and Wheels in the middle. They both carefully install the antenna, assisting each other as required, and then fasten 6 bolts to hold it for landing. You're about to see a video of Wheels installing one of the bolts here. He works pretty low in the shuttle payload bay while Scott stays higher up near the sill. Now both of them are free float, and they begin working on the power and data grapple fixture on the port side of the payload bay. They release 4 fasteners, and then they both carry it over to Node 2 Harmony, which is still in the bay. This grapple fixture couldn't be launched in place, so the EV crew will tie it down with tethers onto Node 2, and it will take a ride over to the space station after EVA-1, when Canadarm grapples a different fixture and moves Harmony over. And here you can see its temporary tie-down location for that ride. It's held in place by adjustable EVA tethers. There's more prep work to ready Harmony in the aft part of the payload bay. Previously, Scott had released 2 connectors that would be difficult to reach later, and now they'll be removing 8 hard contamination covers from the ring on the berthing surface on the left. They'll also be removing 6 caps from under that large strip of insulation that's flashing on the right. The last thing they'll do in the payload bay is remove the launched activation cable that's connecting Node 2 to the shuttle payload bay. Up until it's disconnected, Harmony is receiving power to keep its heaters activated, but it must be disconnected for its move over to space station. When the cable's removed, Scott takes it back to the airlock with him. When the EV crew are clear, Node 2 can be grappled and unberthed for its ride to ISS. Both crew members head to the airlock for some logistics, and then they split up somewhat. Scott goes up to the interface between the Z1 and P6 truss elements to disconnect 4 fluid lines, and that's where the video is flying right now. This is the first step in preparing P6 for removal from Z1. So here's the work site covered by a shroud. Scott has to temporarily remove that shroud, and then he disconnects the ammonia-filled fluid umbilicals from P6 and mates them to Z1. He'll need to be in a foot restraint for many of the operations so he can work with the stiff fluid lines. Here you can see him demating and mating the lines in the Neutral Buoyancy Laboratory. I'll point out, though, in the water, the lines are made of a plastic tubing and aren't nearly as stiff as the real lines. Here he's moving a connector to Z1. At the end of the procedure, he'll be replacing the shroud he previously removed on the Z1 side of the interface. Meanwhile, Wheels has been busy getting a shroud ready to cover up the aft radiator on P6. This shroud starts off in a small bundle on the nadir end, and there are long straps that Wheels deploys from the nadir side to the zenith side of the radiator that are used as guides for the shroud. And you can see him here with the strap. When Scott gets there, they each take a side of the shroud and pull it up to cover up the radiator. Then they take 2 smaller shrouds up to the top of the P6 truss and install them on 2 boxes called the sequential shunt units. These boxes would get too cold while P6 is being relocated, so the crew installs shrouds on them to keep them warm. Later, after P6 is relocated and reactivated out on the end of the truss, the crew will need to remove them so the boxes don't get too hot. Here they're installing the starboard shroud first, followed by the port shroud. On the way into the airlock, Scott cleans up the antenna worksite by mating a connector, and then they ingress, Wheels going in first. So at the end of the EVA, the S-band antenna is in the payload bay. Harmony is in transit on its way up to the port side of Node 1, and about half the preparations for P6 relocation are complete. After EVA-1, the crew is working on installing Node 2 onto Node 1, getting the suits and tools ready for EVA-2, and getting the space station robotic arm in position for P6 relocation. The second spacewalk is performed on Flight Day 6 by Scott and Dan, and it's expected to be a 6.5-hour EVA. So let's roll the video for that second EVA. On this EVA, Dan egresses the airlock, and then Scott comes out second. The first main objective is to detach P6 from Z1, so the arm grapples P6, and Scott and Dan begin demating cables right after getting out of the hatch. There are 9 cables, which answers the earlier question, that need to be demated in order for P6 to separate from Z1. Dan generally stays high, and you can see him up in the upper part here, and Scott stays low. They're actually swapping cables for caps that have been stowed on Z1. Some of the cables might be a little stiff, but for most of them, the major task is really getting them tucked close to structure at the end of the procedure. After that, Scott closes a capture latch to hold P6 onto Z1 while they go around the P6-Z1 interface, disconnecting grounding strap bolts and demating the 4 main bolts that have been holding P6 onto Z1 since it was first installed. These are called RTAS bolts. RTAS stands for Rocketdyne Truss Attachment System. And we're planning to use a ratchet wrench with a handle extension to break the torque on these main bolts. After the last bolt's removed, Scott opens the capture claw, and Stephanie and Wheels move P6 up away from Z1 using Canada Arm 2 for its first move in the relocation process. After this, the EV crew members separate, and Dan goes up onto the truss to perform 3 short but important tasks. First, he goes to the starboard S1 truss element. Here he'll be reconfiguring some connectors for a squib firing unit. The connectors are located between the S1 radiator beam here in the foreground and the S1 truss, which as we rotate around will be on his left. After performing this connector swap, the S1 outboard radiators can later be deployed using ground commands. Then Dan heads to the S0 truss, and he actually enters into the truss. In the truss, there are electrical lines that need to be rerouted so P6 can be activated when it's out on P6. You can see the flashing connectors in the zenith and nadir parts of this bay. Although it's a tight squeeze, we've sent crew members into this bay previously to perform similar reconfigurations. And Dan just needs to use caution not to bump into lines and connectors while he's inside the truss. Then he'll egress the truss and begin heading off to his third task in this string of EVA tasks. That task is the change out of the critical power control box. This box needs to be exchanged with a new box before the station robotic arm can use a grapple fixture on Node 2 Harmony as its base. Meanwhile, Scott went over to Node 2, which is newly installed onto the port side of Node 1. Node 2 needs to be externally outfitted and readied for future spacewalks and berthing operations on its ports. At the end of the EVA, Dan comes over and helps with this outfitting as well. The newly installed items are 11 handrails, 2 straps called gap spanners, 3 worksite interfaces or WIFs, an electrical connector, and 5 small trunnion and keel pin covers. They brought these items over in bags that they prepped inside, pulling them out 2 or 3 items at a time to save trips. Scott will also remove 4 pins, 1 from each of the radial berthing mechanisms, and he'll release the zenithmost berthing pedal launch restraints. They'll also remove 16 caps from under the large MLI covers that you see flashing on the right. When Dan gets done on the truss, Scott will stop work temporarily on this outfitting, and then he and Dan will detach the grapple fixture that they'd installed on Harmony for its ride to space station. It's been held on by tethers since EVA 1. Together they move it down to the nadir side of Node 2, where you can see that flashing ring. They'll install 4 fasteners to hold it in place and then attach 2 connectors that were previously loosened in the payload bay. This later allows the SSRMS to be based on this grapple fixture for future robotics operations. At the end of the EVA, they both take their empty bags back to the airlock. Scott will go into the airlock first, followed by Dan. So at the end of this EVA, P6 is in transit, and Dan's next EVA will be in the stage with Peggy a few days after shuttle undocking. After EVA 2, the crew works on relocating P6 down to the port end of the truss, just shy of berthing it onto P5. The third spacewalk is performed on flight day 8 by Scott and Wheels, and it's expected to be a 7-hour EVA. Let's roll the video for EVA 3. Again, we'll start by zooming in on the airlock quest. This time, Wheels will egress first, followed by Scott, which spreads the experience of operating the hatch amongst the crew. After they come out of the hatch, they have a long way to travel to get down to P5 so they can assist with P6 installation. You can see P6 flashing all the way down the truss on the right. We'll fly the virtual reality simulator down there, and when we get there, you'll see that P6 is positioned just off of P5. In flight, it will be 130 centimeters out and 2 meters forward. Due to the required precision to install the truss and the need to monitor the robotic clearances, the EVA crew is required for berthing cues to help the robotic operators with the fine details. As we fly up, you'll see Scott in the foreground at the nadir forward corner, and Wheels is in the aft zenith. The crew is going to flash here for a second. They'll give verbal guidance for berthing, and then Wheels will close the capture claw. After this, they'll go around to each corner and install the RTAS bolts in a specific sequence, ending with a sequence using a torque wrench. And then they'll release the preload on the capture latch so that the bolts carry the primary load for the life of space station. The next major objective will be to apply power to P6 so it can be activated and its arrays can be redeployed. This is done with 4 umbilicals. So Scott begins mating the connectors from P5 to P6. As we fly around here, you'll be able to see the area they're working in. It's going to be flashing. Scott's in a foot restraint due to the cable stiffness and the geometry in the area. Here's some video from the Neutral Buoyancy Laboratory, so you can see the general worksite. Wheels will come over at the end of the procedure to help Scott as required. Next, they'll go to the very tip of the newly installed truss element and take the shrouds off of the sequential shunt units. These are the same shrouds that were installed on EVA-1. They put these in a bag to bring inside, and then Wheels heads back to the lab to start working on the MBSU task. Scott stays behind and releases the cinches on the photovoltaic radiator so that it can be redeployed as part of the P6 activation steps. Once the cinches are released, the radiator will be deployed with a command from the ground. The radiator is deployed during a day pass, so it can be watched for any unusual movement or problems. Scott might or might not be in the area depending on his timing. Next, Scott heads back to the starboard truss. Between EVAs 2 and 3, the ground sent commands to fire the cinches on the S1 outboard radiators, and these radiators should be deployed by this EVA, although it isn't shown that way in this video. Now that the radiator cinches have fired, Scott reconfigures the squib firing unit back to the way we found it by swapping a connector and cap. Then Scott will have some free time where he can perform some small get-aheads like bag moves and strap installations. And now back to what Wheels has been doing since he last left Scott on P5. He sets up the shuttle robotic arm with an adapter and a foot restraint, and he gets onto that foot restraint over on the nadir lab. He might have to direct George and Stephanie, the arm drivers, with cues for moving the arm. Here you can see him coming into the upper part of the screen. They then fly Wheels over to the shuttle payload bay on the starboard side to pick up the critical spare box called the main bus switching unit, MBSU. He drives 1 bolt to release it, and then takes it back to space station via the shuttle arm. Scott's waiting for Wheels to arrive so they can both install it on external stowage platform 2. Wheels needs Scott's help because the arm can't quite reach for Wheels to install it by himself. Here you can get a feel for the size of the box, which weighs 525 pounds. After that, Wheels will take the foot restraint off of the shuttle arm, and they'll both come inside, Scott going into the airlock first. Right around this time, the first solar array will be redeploying on P6, so the day is still pretty busy for the IVA crew after the EVA. After EVA 3, the arrays should be deployed that same day, so the crew can get ready for their next EVA 2 days later. As you've heard, we might insert a spacewalk after EVA 3 for a towel repair test, but I'll talk about that one later. Next, I'll talk about the Peggy and Yuri EVA, which is expected to be a 6.5-hour EVA. So let's roll that video. Here you can see the P6 solar arrays newly deployed on the far right-hand side. On this EVA, Peggy will come out of the hatch first, followed by Yuri. They'll both make their way to the forward end of the lab. Peggy's operating on the left side of the screen and Yuri's on the right. The main objective here is to clear the area of cables and obstructions for the eventual installation of Node 2 and some fluid trays. The first task they work on is demating the Spitz power transfer cables. And next they'll disconnect 8 cables that run between the pressurized mating adapter and the lab, and they'll temporarily tie those off. After that, they demate connectors on the rigid umbilicals on each side of the lab, temporarily stowing them out of the way on the lab and other places. These need to be removed so that they're accessible once fluid umbilical trays are installed on top of these during the stage after the Node 2 move. Here Peggy's working on some of those cables. During this time, Yuri will also be installing caps on his side of the lab to cap the receptacles left open by the PMA cable demates. And Peggy will also remove a light that will later be in the way of those trays. You can see it flashing here on the left. After the new trays are installed on top of these, the light can be reinstalled. Here's Peggy with the light headed to the airlock. Near where this handrail is flashing, Yuri will go up onto the truss and configure the port squib firing unit for deploy of the P1 outboard radiators. He also might loosen some bolts for the next flight while he's in the area if there's time. Next, they both head down to Node 2 to remove the active common berthing mechanism cover. It's the ACBM cover. This cover's been protecting the sealing surface and mechanisms, but now it must be removed to allow the pressurized mating adapter to be berthed. The cover is held on by a strap that goes around the circumference. So after loosening the strap, they work together to bundle it up. And you can see at first here they're halving it somewhat. Then they'll use wire ties to get the bundle fairly tight. And there's no right or wrong way to do this. Whatever works is what we're going to go with. And then the shroud will be taken back to the airlock where it can be put into the progress as trash. Next, Yuri travels back behind the Z1 truss almost to the Russian segment. And here he'll be taking an electrical jumper out of the system in order to reconfigure a power system. And a similar task was done in the vicinity on STS-116. At the same time, Peggy will be performing a different configuration over in a starboard part of what we call the rat's nest. Here she'll be working with a power cable that was previously wire-tied on the S0 aft tray. This is the general vicinity of the connectors. When she's done with the cables, she'll be retrieving a box called the baseband signal processor so it can be upgraded on the ground. She brings that into the airlock. And lastly, there's some bag and tool reconfigurations that are required to help shorten the stage EVAs that immediately follow this flight. They transfer tools between the bags and move a bag to the S0 truss. After the CVA, the station will be ready for moving the pressurized mating adapter and Node 2 after the shuttle departs. Another EVA that you've been hearing about this morning is still in the approval process, and it's dedicated to the testing of tile repair material. If approved, this EVA will be inserted between EVAs 3 and 4, and it will be performed by Scott Perzynski and Doug Wheelock. For this EVA, we chose our shuttle crew members who are already trained in tile repair. And we're glad to have Scott on board because he's been involved with the tile repair efforts since return to flight. For the most part, he'll be primed for performing the test, although I will say that we haven't worked out the exact choreography with he and Wheels. If approved, we'll call the Spacewalk EVA 4, and the Peggy and Yuri EVA will be called EVA 5. We chose to insert this EVA rather than putting it at the end of the flight for a couple reasons. First off, spacesuit logistics are a little bit easier because Scott and Wheels are performing EVA 3. If they also perform EVA 4, then we don't need to swap spacesuits in and out of the airlock as much. And also, if for some reason the orbiter has to depart or we have some other contingencies, then that EVA 5, the Peggy Yuri EVA, can be deferred to the stage because Peggy and Yuri are going to be there during the stage. The material we're testing is called STA-54, and the STA stands for Shuttle Tile Ablator. The crew takes it outside in a container called the Tile Repair Ablator Dispenser, also known as the TRAD. The material is stored in the TRAD in 2 parts. We call them parts A and B. When the crew pressurizes the system out, EVA, the 2 parts begin to mix, and the material can be dispensed out of a gun. It's a pinkish orange and sort of a creamy peanut butter consistency when it's applied by the astronaut during a spacewalk. But over time, the two parts react, and the material begins to thicken, reaching full hardness in about 24 to 48 hours prior to shuttle reentry. The astronaut applying it has about an hour to shape the repair, depending on the thermal environment, until it hardens so much that it can't easily be worked. We're doing this test because we've been able to accumulate enough data on the re-entry properties of the ablator material to believe it's going to perform well on entry. But we'd still like to demonstrate how well an astronaut can apply the material during a spacewalk. The specific open questions about space application have to do with a combined vacuum and microgravity environment in which it's applied. For example, we expect the ablator material to bubble when applied in space, as it does in vacuum chambers on the ground, but we don't yet have proof as to how many bubbles will get in a hard vacuum or how they'll distribute or combine within the material in microgravity. The bubbles will likely cause the material to swell slightly like a bread loaf, and we aren't sure how much of the swelling can be flattened down using the foam tools that we have to shape the repair. So can I get the series of photos that I selected? First, this is the TRAD. Weighs about 50 pounds, and it's the size of 2 or 3 large coffee cans stacked on each other. You can see the hose and the gun here in the foreground. Next photo. Here you see a repair that we made in a vacuum chamber a couple of years ago using STA-54. On the surface of the repair, you can see some bubbling, and here on the ground, some of the bubbles have risen to the surface and are popping. Next photo. Here's a sample we made in a vacuum chamber on the ground that's been cut open. This particular sample shows a pretty dramatic difference between the surface bubbles and those near the bottom. Not all the samples are this way. The final density and bubble distribution can depend on many things, including temperature. If the material is applied warm, it's creamier and the bubbles can more easily rise to the surface. And if it's applied colder, the material stiffens right away and the bubbles can't move around as much. Next photo. On the test on this flight, the crew will take a sample bag out of the airlock with them. On the left side of the bag in this photo, you can see a hinged door that folds down over 2 boxes. And each of those boxes will house an array of tile samples that the crew will fill. Next photo. Here's the set of samples that we'll be doing. Each sample will undergo extensive ground testing after the flight to determine how well the repair was applied. Some of the samples are machined-looking squares or cylinders where we conduct specific experiments, for example, bubbling and tile adhesion tests, and others are impact test articles or replicas of real damage. That's the last photo, if I could get the video. This video shows the location of the TRAD during a repair. The crew member doing the repair wears it under the backpack so that it floats loosely. We don't want it in front or else it might bump the delicate tiles on the shuttle. Next is some KC-135 zero-G aircraft footage from the return to flight time frame with a suited crew member. We only have about 25 seconds of free fall at a time as the aircraft goes through a parabolic pattern, alternating 0G and 2G pullouts. So we're pretty rushed when we're doing these repairs on the plane. And this, we're still on the KC-135, this time doing an inverted test where the subject laid on their back. The purpose of this test was to verify good adhesion to tile. We applied 3 dollops, and you can see an interesting ice cream cone effect in microgravity. Then the 0G aircraft did a 2G pullout, which we time-elapse here, and then we could see which areas stuck well enough to hold the material onto the tile. We also repeated the experiment, tamping with foam tools to see if that assisted with adhesion. In general, over our test series, we found that light tamping was better than no tamping. Now we're actually performing a repair. This is similar to what we'll be doing during the in-flight test, except that this is a pretty large cavity. You can see the bulging of the material on the sides, and remember this isn't caused by gravity since we're free-falling on the aircraft. This is video footage from the human thermal vacuum chamber. In this facility, we put a crew member in a flight-rated spacesuit in a thermally controlled chamber. Here you can see the material as it comes out of the gun. And now the crew member is tamping the material to smooth the surface. And you can see that tamping is pretty effective. We can't keep the foam touching the STA-54 for very long periods of time or else the material will stick to the foam, but light padding usually does the trick. After a few minutes, we came back to the sample, and you can see that it's bubbling. In 1G, the bubbles rose to the surface and popped. In 0G, we expect the material to swell rather than having a lot of bubbles pop on the surface. Again, light tamping was used to smooth the surface, collapsing some bubbles, popping others. On the DTO, our crew members will need to be keeping on top of their repairs and coming back to smooth previously repaired samples as required. So in this EVA, the crew will come out of the airlock and they'll have with them 2 bags. One bag will have the TRAD with some tools in it, and one bag will have the towel repair samples and some tools. Both crew members will head to a location that we're still working out, but it's probably somewhere in the lab, and they'll set up their tools in their bags. TRAD is then pressurized, and at that point the material begins mixing and setting up or thickening. So we'll purge some out of the gun to start getting a good mix. We'll work on a sample. We'll purge some out of the gun. We'll work on a sample, and so on. We'll be watching for material swell and going back to previously completed samples as required to keep the repairs looking fairly flat as they bubble or swell. And when we're done, we'll take the TRAD, some tools, and the samples down to the shuttle payload bay and put them into the tool stowage assemblies for landing. And then the crew comes back in so we can all get ready for the 5th EVA that will be happening that day, or that next day. This EVA, this particular TRAD DTO EVA, is expected to take about 4 hours or so. So now I have some show and tell. I'm going to put on a couple of gloves. First, I'm going to show you a prototype gun. It's not exactly the same gun that we use for TRAD, but it's pretty close. So this is what the gun looks like. There are swivels at the base to allow for good movement for the crew member, and it has an auxiliary handle for the crew member to specifically dispense the STA-54 right in the right spot, right where he wants it. The material comes up through the handle, and our crew member can squeeze the trigger like so, and the material will come out the tip. And then when the trigger is released, the material will stop coming out of the tip. And that's what the gun looks like. Okay, next I would like to talk about foam. Partway into our testing a few years ago, we discovered that open cell foam doesn't stick to the STA-54. And this was kind of a big deal for us because we were trying to determine how we were going to shape the repairs. Now, the open cell foam doesn't stick to the ablator, but only if you just use very light, quick motions, padding motions, and we call it tamping. This particular item is called an angled stamp, and it's one of our top choices for padding down a repair. So I'm going to demonstrate that. So here I have in a block of foam, I have some of the Part A only of the STA-54. And you can see that the foam is very effective in tamping down the material. For smaller foam brushes, we use a caddy to carry them. And so I'm going to talk about one piece of equipment that we'll take outside with us. This is a half gel, half foam brush caddy, and it has a removable EVA handle in it. We keep the foam tips in these slots, and I've got one of the slots outfitted. We can just attach the handle and pull out the foam tip. And then when we're done with our foam tip, and if we want to retrieve another one, the handle can be removed, and the tip remains tethered inside the bag. Okay. I also have a sample of the hardened STA-54, and I'm going to hold it up. Maybe the camera can zoom in on it. This was done on the ground in a vacuum chamber, and I specifically brought this one to show you how the bubbles in this case did not distribute such that all the bubbles were at the top. This is a more uniform distribution, and I don't recall the exact case for this particular sample, but possibly it was dispensed very cold, and the bubbles didn't have a chance to move around and settle to the top. Okay. And lastly, I have a repaired sample, and this is what a real repair might look like. In it, you can see the gray areas. This is actually a mittens primer coating or a mittens wash, which is another type of repair that we have available. And we apply that first before applying the ST54, just to make sure that that the ST54 is going to adhere well to the tile. So apply that first, and also the mittens wash coating also helps to repair the shallower areas that we're not going to fill with ST54. And I'll point out that the ST54 is underfilled. You know, the cavity is not completely filled to the top. And that's because the material will on entry swell a little bit. And we don't want it to swell so much on entry that it comes up over the top of the surface of the tile too much and trips the boundary layer for the shuttle. So with that, I have just one more parting thing. And that's that Scott and I are both very lucky to be working on this mission and this test, because he and I both participated in the tile repair development effort for years. And I also wanted to point out that we were not alone in working on this development effort at the technical level. Were Dana Weigel, Dr. Mike Fowler, Laura Bailey, John Cowell, and Ben Green, just to name a few. And Dr. Fowler is our STA-54 expert. And if you have questions I can't answer, then we'll be able to write those down and get those to you after the briefing associated with the material. That's all I have for EVAs. So, Rob?
Thanks, Dina. That was very interesting. We'll take questions here in Houston. We have about 25 minutes for questions from here and the other centers, so we'll whip around as quickly as possible and start with Mark.
Thanks. Mark Carreau from the Houston Chronicle. Can you tell us volume-wise about how much of the STA you'll take on this run, and how you probably have some idea of whether, you know, how far that could go in tile repairs? Could it repair theoretically, you know, one large divot, or could you spread that material among, you know, several if you had to on a mission? Just give us some sense of what this volume in your test would do in an actual case, if you could. Thank you.
Okay. The TRAD holds about 70 to 100 usable cubic inches worth of STA-54. And so the way I like to think about it is tiles are generally about 6 by 6 on the bottom of the orbiter. And you know, if you take 6 by 6, that's 36 inches. And so maybe you could fill a couple inches tall. So if we had a loss of a tile, something to that effect, maybe a little bit larger, a little bit more volume than that. We're probably going to end up using most of our volume on the test, although we haven't yet calculated all of our purges, everything that we want to accomplish during the DTO itself. You know, there's 10 samples, and then if we're going to purge once between each or twice between each, and we're still working out those details. So in any case, that's about how much volume is in the TRAD, and it's we're probably going to use all of it.
Thank you. Tarek Malik with Space.com and Space News, and I guess two short ones, and the first one would follow Mark's question. On the, I guess, the repair test on that spacewalk, you showed us, I guess, the emittance wash primer and the STA-54. Is that something that you would actually test out, to both of those things, to see how they work together?
Well, if I'll hold this up again. So again, the gray is the mittens primer coating, and we're going to, on the ground, install the mittens primer coating. And so we won't be doing that operation during the actual DTO. We'll only be installing or dispensing the STA-54. And that's because we've already demonstrated that we can apply the mittens primer coating, so we just don't want to spend the time to do that.
Then a short follow-up to the earlier, the P6 install or relocation. I was just curious what the clearances they're going to be really looking at when they're kind of guiding the robotics folks in. Is it just a few inches? Is it just kind of to make sure everything is not whacking any hardware? You know, what are you looking at there?
Well, this is not like on a previous mission where we just have, I don't recall, but just a few short, small inches. It's really a matter of not having visual cues for the robotics operators. So we don't really have very, very small clearances in this particular case.
Gina Sinceri, ABC News. How are the samples of damage chosen to go up? These are simulate damage you've seen in the past or worst case scenario?
Okay. This has been a really long effort. You know, we've been dreaming of this DTO for quite some time, and so some of these have been conceived of a long time ago. Maybe I'll just take a few, for example. The cylinders were chosen because we really wanted to measure or understand the density, how the bubbles distribute. And so in that particular case, just a machined out cup was kind of used as the thinking, something very simple that doesn't take up much volume. In that case, we'll dispense some and we won't tamp it. And then on the other one, we'll dispense some and we will tamp it. We'll see if we can make a difference from an EVA perspective. Also, we have adhesion samples that we're going to bring back, and right now we're debating what exactly we're going to do with each of these, but we might pull test it to see approximately what percentage adhere to the tile. We have a 6x6 tile with a 4x4 sort of cutout, and the reason we have that one to fill is that earlier on when we were doing material properties testing in the ArcJet facility, that's what they looked like. And so we want to create one on orbit to make it look just like we would on the ground and see if it also has the same characteristics. So those are kind of like the experimental type things. Additionally, we obviously want to repair realistic looking damages. And so we've chosen an ice impact sample from actual ice impact testing. Thank you, Stephanie, for bringing that up. And you can see in that the light blue sample right there. It's kind of a narrow sample, so might be a little bit more challenging for our EV crews, something to give them a challenge. And then the smaller damage samples, the purple that you see, are mimicking the STS-118 damage, and you see that in the upper right-hand corner. And then we'll have a larger deep damage as well in between those two. So we're trying to get a variety of both experimental and just demonstrating our capability to enact a real repair.
And after 120 returns, how soon will you get your hands on it, and how long will it be before you can report back to us on how well it worked?
Well, I'm actually not sure about that. I'll have to get you that answer when we'll be able to take those out of the tool stowage assemblies and, process it. So I'll get that for you.
Todd Halverson of Florida Today on a different subject. Could you refresh my memory on how a manual deploy of a solar array wing would be done if the motors didn't work? What type of tool would be used and what the procedure would be?
Sure. So a manual deploy is done by driving a bolt, which actuates a motor. So instead of having the motor drive automatically, the crewman reuses his pistol grip tool with a socket extension on it. And it takes many turns. I think it's over 2,000 turns in order to deploy it. And again, a couple of batteries. So anyway, that's the general gist of the tools.
And on the STA-54, is there a toxicity issue and for bringing it back into the cabin? I assume you're stowing it in the payload bay, but if any of it got on a suit or gloves, is there an issue?
Well, there's two things to talk about toxicity-wise with TRAD. First, I'll answer your question directly, and that is that a byproduct of the reaction of the parts A and B when they mix is ethanol. And so the space station folks don't want us to bring in ethanol in large quantities. I don't believe that's from a toxicity perspective. I'm not actually sure what the exact constraint is with it, but we are unable to scrub that out adequately. And so rather than try to understand the exact quantities that we're going to have to bring in and whether or not this would be acceptable, what we opted to do was just stow whatever we have remaining into the tool stowage assembly. I don't believe a small quantity, for example, if we got some on the gloves, is going to be an issue. It's mostly just the larger quantities, like actually bringing in a full TRAD or maybe a partially depleted TRAD, the tile samples, and that sort of thing. But I'll just say that we have a little bit of forward work to figure out what would be the maximum quantity we could bring in and still make the space station folks happy. Did you want to hear about the other toxicity concern? Sure. Okay. The other toxicity concern is it has to do with the parts A and B. Part B is it can separate, especially in shipping and that sort of thing. And if it separates, the catalyst, it's called A1100, can can be corrosive to the eyes and skin. So we have a bunch of steps to ensure that we thoroughly inspect the bag before we open the TRAD. We know where to look before we would allow a crew member to touch it, and we would be able to see that in advance. So we feel really good that we've certainly, we're not going to expose our crew members to any sort of toxicity concerns on the TRAD before it goes outside.
Todd, did you have another follow-up?
Yeah, just one, please. On the QD disconnects that they're going to do, I believe, on Z1, is there a potential for residual ammonia to leak there, and what precautions might you take?
There is potential for that, and so we, as we've done in the past for potential leaky ammonia cases, the crew's been trained on how to use a system in which we can detect whether or not they've brought ammonia into the airlock. And so, first of all, what happens if the fluid QDs leak is that on the ground we'll have a bake-out calculator. We'll determine, whether or not the ammonia has come off the suit adequately before we go into the airlock, and we'll reserve enough time to do a test and do a complete repress cycle if required to make sure that before we come in that we're adequately scrubbed. And then there are other precautionary things that we can do on the inside as well, like have masks available and wet towels and that sort of thing for IVA contamination if required.
Bill.
Bill Harwood with CBS. A couple of quick ones from me. It's not intuitive to me what happens to how the bubbles will behave in zero-G and with those temperature constraints, but obviously they don't rise to the top. But does the tamping, does that effectively push bubbles out, if you see what I'm saying? I mean, is that what tamping does primarily, is help minimize bubbles?
Well, the tamping is used for maybe three reasons. It's used to shape the repair, so the ice cream scoop like you saw. It's used also to help with adhesion, and then we believe that it might flatten some of the bubbles, although, it'd be kind of like a waterbed. We're kind of thinking it might swell like a bread loaf, and you push on one side and it kind of rises on the other. And so I think that that's part of the demonstration we want to learn is how effective is the tamping at getting rid of some of the swelling.
Understood, thanks. And on the P6 stuff, just to follow Todd, can you go over what you see as viable contingency ops for P6 deploy? I mean, just from an access standpoint, other than cutting guide wires or manually driving the motor, is there anything else they have practiced for?
Yeah, they've had the full gamut of all solar array contingencies. There's some that are not really related to necessarily the issues that we've seen on 12A.1 and on 13A. So maybe I'll stick with those. But specifically, the grommet issue, if we were to have a grommet issue, but I think we've explained that we don't believe there will be a grommet issue. But if we were to have one, for example, we know of a specific fray, I don't recall now, but I think it's between like 11 and 12 bays deployed, something like that in our procedure. We might be able to retract the array down to the level where the crew member is located, and then we would sort of fluff the panels such that we would have exactly the correct number of panels, I think it's 16 or 17, above the fray, and the other amount of panels below the frayed area, and then attempt to redeploy. So that's one example of something that we might be able to do, related to that sort of thing.
Go ahead. Is that it, though? Is that pretty much covers it, that in the manual drive of the motor?
We also, have contingencies to latch and unlatch the boxes and put it into high tension mode. Well, the classes are like 2 hours long, and of course I'm drawing a blank on what else we have. But we also have we do have other tools that we can use for, retraction, or redeploy contingencies. For example, to re-spool, like on 4A, they had a problem on their array deploy. These are the same arrays, by the way. And so the crew's been trained on how to re-spool the arrays in order to allow them to deploy.
Thanks. One maybe a little simpler question, or easier for you to answer. Could you just prioritize as an EVA trainer the complexity? I'm looking at task complexity. How do you see them as the most difficult, second most? I mean, just give us some sense of what's harder for those guys.
Out of all the EVA tasks, you mean? Yes. Okay, well, in my mind, I'll just say that one of the most complex, detailed tasks is going to be the tile repair DTO. And that's just because there's a lot of real-time discussion that's going to happen depending on what how the material behaves. So we'll have to make decisions at the time. We'll have to say, well, we're going to need another purge here, or it's rising. I think we should not add any more material. I think we should. And so I think there'll be some complexities associated with that. On EVA-1, the complexities are associated with the fact that we are working with fluid QDs that have been mated for quite some time, for almost 7 years. And so we would worry about any leakage there. And so there's some complexities associated with the contingency operations that we might have. Also, I'll say that EVA-3 is a long EVA. It's 7 hours. And I wouldn't say it's necessarily extremely complex, but we just have a lot to get done in that particular EVA. So I guess in my mind, those are the top priorities of things that we worry about.
Okay, let's go to NASA headquarters in Washington for questions.
Tracy Watson, USA Today. A couple from me, and I apologize if these were covered earlier. I had to miss the last briefing. I'm wondering what you can tell us about the cut glove incident on the last flight. I understand it's been determined it was a sharp edge and not wear, and if that's right, how you're going to respond on this flight.
Well, obviously we're taking it really seriously. We've done microscopic inspections of both Beamer's glove from 12.8.1 and the last flight 13.8.1 Rick's glove. And as you mentioned, we have determined that they're cut as opposed to worn. And so we've done a lot of video analysis as well in order to try to understand, is there a particular location on space station that's potentially causing the issue? And really, it's been inconclusive. And so we have determined some areas where the two crew members have both been, but it's quite a large area. It's quite a large amount that they're covering. And so what we're doing on this flight is we're really increasing the quantity of inspections that we're doing, more than doubling the amount of glove inspections. So specifically, I have a glove here anticipating this question. And specifically, both cuts were located right here on the glove, one on each hand. Rick had one hand, and Beamer had it on the other. And so we'll be having the crew look at their glove TMG a lot more often at each day and night cycle. They'll be doing a very thorough inspection, and I have this glove, sorry for only those here at JSC, of course, to see, but this one has got a couple of cuts in it for crew training to show them what it's like. And they'll be doing these glove inspections every day night pass, so that's about every 45 minutes. And then also, after any significant translation that they do, we're going to do an additional inspection. So this is above and beyond what we were already doing on 13.8.1. And we have a termination criteria for our EVA, same as 13.8.1 did. And we will terminate the EVAs if we see a hole in the Vectran. So additionally on this flight, another part of our risk mitigation is to fly an additional set of gloves for each of the crew members that are performing more than 3 EVAs. And so Scott's performing 4 EVAs, Wheels is performing 3. Peggy and Dan are each only performing 1 EVA, but on the stage they're performing 2. So they're going to count as requiring additional gloves. The one thing is that Scott and Wheels are able to wear the same pair of backup gloves. So they each have 2 pairs of gloves, and then they'll share the 3rd pair. But that's kind of how we're going to work the glove situation. And so what we'll do after each EVA, in addition to the crew inspections, we're going to take photos, IVA, of the gloves. We have a specific, set of photos that we're requesting, and we're going to send those down to the ground, and those will be analyzed as well to make sure that we understand if there's any worn areas where those might be more susceptible to a glove cut. For example, missing RTV, that top layer, might make it more prone to receiving a Vectran cut, or it's has a little bit less redundancy there. Then we might be able to make a determination that we want to switch to a backup pair of gloves. So we're doing some additional risk mitigation in that area as well. There is a development effort underway to create an overglove, and so this is something that would be worn in that area that I was showing you, in order to give it an additional layer of Vectran. And it's unknown at this point whether or not this will be captured on this flight or some sort of subsequent flight, but it's certainly a long-term mitigation that the EVA program is looking at.
Okay, thanks. And my second question is this. You've described a lot of tasks that sound pretty difficult and very hand-intensive for these guys. And I'm wondering, in the kind of grander world of EVA, how do these 4 or 5 EVAs stack up compared to the EVAs done on other shuttle missions? Thank you.
Well, I'd say these are about the same. We did look at this particular flight and try to, determine are there any non-hand intensive, flight or EVAs, and we determined that you're right; these are fairly hand-intensive EVAs, but I wouldn't classify them as out of the ordinary for what we've seen in the past.
Okay, let's go to the Kennedy Space Center for questions.
Yes, Marcia Dunn with the Associated Press. I'm wondering how long the actual tile repair demo will take. How much time do you expect that to take, and how much time for the whole spacewalk from beginning to end? And I'm wondering if there are any kind of suit problems that cannot be fixed or replaced, or if one of the 2 shuttle spacewalkers just can't go out. Could the space station spacewalkers step in and do some of this work?
So the task is expected to take, the task itself is expected to take about 3 hours. And I will say that our detailed timeline is not written, though. And the entire EVA is expected to take about 4 hours or so. And we're trying to keep it minimized to just that one task on this EVA, because we have to go out the next day and perform a critical space station EVA on EVA 5. So we need to get back in, swap the suits, and get ready for Peggy and Yuri's EVA. So we are also limiting that time and not adding in space station objectives unless something trumps that, like an ISS contingency. The second part of the question.
Could Yuri and Peggy do this TRAD activity?
Well, I guess we hadn't really thought of that. There's nothing particularly. The only problem is they're not really trained on it, and there's quite a few intricacies. So trying to train them, I guess we'd have to determine how much time we would have available to make sure that they understood all the intricacies of operating the hardware before they went out. But they haven't been specifically trained on it.
Okay, that's all the questions from the Kennedy Space Center. With that, we'll wrap it up with a quick programming note coming up next on NASA Television. At 1 p.m. Central Time, 2 p.m. Eastern Time, the STS-120 Crew News Conference. So we'll see you back for that. Thanks a lot for attending.